Okay, today we're gonna continue with finite fields. So just a review of last time, a finite field. Let's jump to the proposition. Proposition 15, we proved last time, any finite field is isomorphic to fp to the n for some prime p and some integer n. So you give me, you tell me you have a finite field, and then just tell me what is the cardinality of this finite field. It's going to have to be a prime power p to the n. So this is what this is saying. Any finite field is isomorphic to the unique finite field of order p to the n for some prime p and some integer n. Furthermore, this finite field, fp to the n, is the splitting field over fp of the polynomial x to the p to the n minus x, with cyclic Galois group of order n generated by the Frobenius automorphism sigma p. Finally, the subfields of this finite field of order p to the n are all Galois over the prime subfield fp, and are in one-to-one correspondence with the divisors d of n. They are the fields f sub p to the d, the isomorphic to the unique field of order p to the d. They're the fixed fields of the dth iterate of the Frobenius automorphism. So proposition 15 is telling you all about the structure of a finite field, and the only thing that you're deducing all of this from is just the order of the finite field. So you give me a finite field of a specific order, I can tell you exactly what it's isomorphic to, present it as a splitting field of a certain polynomial, tell you exactly what its Galois group is, a generator of the Galois group, and tell you all of its subfields. So that's pretty cool, just based off of the cardinality. And then we proved this application, corollary 16, the irreducible polynomial x to the fourth plus 1 is reducible modulo every prime p. So that was a cool application of this result. The last thing we talked about was proposition 17, the fact that the field f p to the n sub p to the n is simple, meaning you can write it as just adjoining a single new element, theta, to the prime subfield fp. So again, why is proposition 17 true? Why is the finite field fp to the n simple? Well, this is based off of this result, which says that a finite subgroup of the multiplicative group of a field is always cyclic. So therefore, the multiplicative group of a finite field is cyclic and thus has a generator. And therefore, this generator, when you adjoin it to the ground field f sub p, is going to generate the whole field f sub p to the n. So the finite fields are simple. And in particular, there exists irreducible polynomials of degree n over the ground field fp for every n greater than or equal to 1. So why is this statement true? This is because what is the minimal polynomial of this thing that you're adjoining? What is the minimal polynomial of theta? The minimal polynomial, it has to be an irreducible polynomial of degree of degree n, which is the degree of the extension, over the ground field fp. So that's what this statement is saying. It's saying that the minimal polynomials serve as irreducible polynomials of degree n over fp. So proposition 17 tells you that finite fields are simple and there are irreducible polynomials of arbitrary degree over prime subfields. All right. Now we're going to go through a bunch of notes which will prove the next theorem, but sort of we're going to prove the theorem before we state the theorem. So let's make some observations. So recall that f sub p to the n, this unique finite field of order p to the n is described as the splitting field of this polynomial x to the p to the n minus x over fp. So this polynomial is not necessarily irreducible. In fact, it's definitely not irreducible, because you can write this as, let me write this as a note, x times x to the p to the n minus 1 minus 1. Right, so you can factor out an x from this guy. So it's definitely not irreducible over this field. But it's still a separable polynomial because, yeah, okay, I'm not going to go into that. But something about finite fields being perfect fields and so on. So it has distinct roots. It has p to the n distinct roots, but it's not necessarily an irreducible polynomial. All right. This previous proposition 17, which describes the finite field fp to the n as a simple extension of fp, that's essentially saying this: fp to sub n, f sub p to the n is this. You can prove that it's separable by taking the derivative, right? Yeah. Yeah. I'm just forgetting that stuff, so I can't comment too much on it. All right. Okay, so this proposition, which presents the finite field as a simple extension of fp, means that you're just taking the polynomial ring with coefficients in fp and modding out by the maximal ideal generated by the minimal polynomial of theta. Right. So these simple extensions are isomorphic to quotients of polynomial rings, where you're quotienting out by the minimal polynomial, or the minimal polynomial of the element you're adjoining. So theta is the generator for this multiplicative group, and m sub theta is the minimal polynomial for theta over fp. All right, so we have this description. By the first description, which is presenting f sub p to the n as the splitting field of x to the p to the n minus x over fp, we know that theta is a root of x to the p to the n minus x. All of the elements of this guy are roots of this guy. So in particular, this generator has to be a root of this guy. So the minimal polynomial has to divide this polynomial. Right? Not only is theta a root, but all of the roots of the minimal polynomial roots of this guy. So the whole minimal polynomial has to divide this polynomial. And finally, the degree of the minimal polynomial has to be n, because n is the degree of the extension. All right, so that's one piece of one thing to note, one observation. So the observation in summary is that the minimal polynomial divides the polynomial that you're taking the splitting field of, and the degree of the minimal polynomial is n, which is the degree of the extension. Okay. Second thing is, now we're going to go in the reverse order a little bit. So in this case, we took the minimal polynomial of the generator and said it divides this x to the p to the n minus x. And in this case, now in this note, we're going to take an arbitrary irreducible polynomial with coefficients in fp and assume that it divides x to the p to the n minus x. And then let d be the degree of this polynomial, and alpha in fp to the n be a root of this arbitrary polynomial, which divides x to the p to the n minus x. Okay, so we have this root of this polynomial which divides the polynomial we're taking the splitting field of. So if you adjoin this root to the ground field, you'll get a sub-extension of the splitting field. You're not adjoin, so this alpha is just a root of this guy, and that okay, so yes, this is indeed a subfield of this guy. But by proposition 15, we know exactly what all the subfields of the splitting field look like. The subfields look like, let's just go back to proposition 15 to see what it said. So it said the subfields of fp to the n are all Galois over fp and are in one-to-one correspondence with the divisors d of n. They are the fields f sub p to the d, the fixed fields of this guy. So the subfields are in one-to-one correspondence with the divisors d of n. And furthermore, d is the degree of this subfield over the ground field. Okay, so back here, these subfields, what is the degree of this field? Well, it's a simple extension, and you're adjoining a root of an irreducible polynomial. So this polynomial has to be the minimal polynomial of the thing that you're adjoining. So the degree of this minimal polynomial is d. So this extension is degree d, and therefore by proposition 15, d has to be a divisor of n, and this extension has to be a Galois extension. In fact, this sub-extension f sub p adjoin alpha is isomorphic to f sub p to the d, the unique field of order p to the d. And since it's Galois, all of the conjugates of this p of x, the minimal polynomial of alpha, are all of the roots of p of x are in this field because it's Galois over this subfield. Okay. All right. Now, finally, let's tie all of this together. Okay. So, no, again, the elements of f sub p to n are just roots of this polynomial x to the p to the n minus x. And now let's group the elements of degree d by the degree d of their minimal polynomial over fp. So what we're doing is we're looking at the p to the n roots of this guy. These are just the elements of the field of order p to the n. And then we're grouping them together by the degree of their minimal polynomial over fp. Okay. Now, if you, okay, does this p of x, does this mean p of x is separable since f sub p of alpha is the splitting field of p of x and it is a Galois extension? Yeah. And if you take a separable polynomial and look at its logically, it means that any factor of this separable polynomial has to be separable as well. Because what are the roots of that factor? Well, they're just roots of this guy. And all of the roots of this guy are distinct, right? Yeah. Okay. So now let's state the proposition because it makes a little bit more sense why we were talking about all those things once you see the proposition. So the proposition is that the polynomial x to the p to the n minus x is precisely the product of all distinct irreducible polynomials in this polynomial ring with coefficients in fp of degree d, where d runs through the divisors of n. So you can write this statement as a factoring of x to the p to the n minus x. We're going to factor this guy, as a bunch of polynomials p of x, where p of x is an irreducible degree d polynomial with coefficients in f sub p. And d runs through the divisors of n. So the proof of proposition 18 is really just these three previous notes. Mainly it's this one, where we're taking the roots of this guy. So let's look at this polynomial x to the p to the n minus x, and then write it as a product of monomials, x minus the roots alpha. But now we're going to look at each of these terms, and if they're in the same one of these groupings, which is we're grouping by these elements by the degree d of their minimal polynomial, say they have this there, then we take all of those and multiply them together, that's in the same group, and that product will give you this minimal polynomial of degree d. So what happened was we factored this guy as a product of minimal polynomials. Yeah. Mhm. Okay. So proposition 18 can be used to produce irreducible polynomials over f sub p recursively. So let's do some examples. The irreducible quadratics over the finite field with two elements are the divisors of x to the 2 to the 2, which is x to the fourth minus x, divided by x times x minus 1. So why is this the case? So we know that, so we're looking at the irreducible quadratics. I have to write stuff down to explain this. So we're looking at the irreducible quadratics. So we want to look at um, n equals 2 at least. We're looking at n equals 2 because, okay, let me just do this. So the prime is 2 and n is equal to 2. The degree is equal to 2. And now let's apply this result. So we get that x to the fourth minus x is a product of, what are the divisors of 2? There are only two divisors of 2. There's d equals 1 and d equals 2, right? So we have the product of irreducible degree 1 polynomials times irreducible degree 2 polynomials. So what are the irreducible degree 1 polynomials? Well, those are just the linear polynomials, and there are only two of them, x and x minus 1. This is, so the irreducible linear polynomials are just x minus alpha, where alpha is in the ground field, f2. So there are only two of them, alpha equals 2, alpha equals 0, and alpha equals 1. So you have alpha equals 0 here and alpha equals 1 here. So these are the two unique, the only two linear polynomials with coefficients in f2 that are irreducible. And now this result says we have to also multiply by the p of x, which are irreducible and degree 2, right? So what we did here is we divided both sides by x times x minus 1, x times x minus 1. And what's left on this side is just the product of the irreducible degree 2 polynomials over f2. And when you do this division, this numerator is degree 4, this denominator, the product is degree 2. So you expect a degree 2 result. Um, so when you do this division, you're supposed to get a degree 2 result, but this product is a product of irreducible degree 2 polynomials, and therefore there's only a single irreducible quadratic over F2. Yeah. So this gives the single polynomial x squared plus x plus 1. And so this example shows that there's exactly one irreducible quadratic over the finite field with 2 elements, and that's x squared plus x plus 1. Okay. If you had something else, let's just test this idea, this result that we got, because like, okay, we have a foolproof proof of this result, but let's try to test it against some attacks, right? So let's give me some other polynomial with coefficients in f sub 2, and I'll show you it's not irreducible. So for example, x squared plus 1, right? Okay, this is some other polynomial of degree 2 with coefficients in f2, but this is actually reducible. This is x plus 1 squared. Why? Because the Frobenius automorphism is like, it means that you can distribute this squaring process. So you can bring the square here and the square here. So you get x squared plus 1 squared, which is 1. So this is not irreducible. And you can do this process, you can do this thing, this type of thing. Yes, the characteristics too. So you can do this type of thing with any degree 2 polynomial that you give me plus yeah, just x squared alone is not irreducible because x squared is x times x. So that's not irreducible. And I can't really think of any other polynomials because the coefficients are so limited, right? Any polynomial is going to be of the form ax squared plus bx plus c, where a, b, and c are in f2. So you only have, if you want this to be quadratic, you need to make a equal to 1, and then you can make b and c equal to 1 and 1 and 0 respectively. But if c is 0, then you can factor out an x from this, and that's not irreducible. So c has to be 1 as well. And now you only get 2 choices. Either b is equal to 0 or b is equal to 1. But if b is equal to 0, you get this option, which is not irreducible. And b equals 1 is the single option that you have. So that's another way to test that, yeah, there's exactly one irreducible quadratic over the finite field of 2 elements. But this is a more general process, and we can keep using this process to get more ideas about what are irreducible polynomials over finite fields. So let's continue the example. Now let's talk about irreducible cubics over the field with 2 elements. Okay, so irreducible cubics, so degree 3 things. So the same thing, what are the divisors of 3? They are 1 and 3. So if we want to find the irreducible cubics, we have to divide by the linear factors. And there are only 2 linear irreducible polynomials. So let's do this again. So this 8 is 2 cubed. That's why we have x to the 8 minus x here. And we divide by all the linear polynomials, irreducible linear polynomials, and we get the product of all of the irreducible cubic polynomials with coefficients in f2. And now since this is degree 6, and anyway, you would expect degree 6 because this is degree 8 minus degree 2, which is degree 6. So since this is degree 6, that's a product of 2 cubics. So there are exactly 2 cubics. And these 2 cubics are x cubed plus x plus 1 and x cubed plus x squared plus 1. You'll see when you multiply these 2 things out, you get this. So the only mysterious process I did here was actually factoring. But you could check that this factorization is correct by multiplying these two things together. Yeah, so x cubed times x cubed is x to the sixth. 1 times 1 is 1, and you can get every other term by multiplying terms here as well. Um, how do you compute x to the 7th minus 1 divided by x minus 1? So you're asking about, wait, why are you asking about x to the 7th? So, okay, here's the question. X to the 7th minus 1 divided by x minus 1. Are you trying to find particular, irreducible polynomials? If so, of what degree, of what base field? The base field has to be F7, right? And you're trying to find the irreducible polynomials. Oh, x to the 8 minus 1. Okay, yeah, my bad. So the base field is 2 again, right? So the base field is F2, and you have x to the 8 minus x over x times x minus 1. So yeah, you're just doing this, right? So this is equal to x to the 7th minus 1 over x minus 1. And yeah, how do you actually do this long division? I'll talk about this a little bit, but basically the answer is there is a way to do it, but I don't know. Yeah, you can check that this works because you can take these two things and multiply them together with coefficients in f sub 2, and you'll see that this works. But how do you actually do the long division? There are algorithms to do this, but yeah, that's all I can say. Does that answer your question? Okay. All right. So yeah, if you take this polynomial and multiply them together with coefficients in F2, you'll see that it actually results into this polynomial. And so this actually does factor into these two polynomials. But is there a more systematic way to go from this polynomial to these two by using some division algorithm? There is, but yeah, I can't give you details about that though. Okay, so the next example is irreducible quadratics over the finite field with two elements. Okay, so these are given by dividing x to the 16th minus x by x times x minus 1, so the linear polynomials, and also the quadratic irreducible polynomials. So we're looking at the quadratics, so that's n equals 4. And what are the divisors of 4? There's 1, 2, and 4. So we have to divide by the linear irreducible polynomials and the quadratic irreducible polynomials. There are two linear irreducible polynomials, x and x minus 1, and there is a single quadratic irreducible polynomial. That's the one that we got here, the single unique quadratic irreducible polynomial over f sub 2. So we divide x to the 16 minus x by x times x minus 1 times a single quadratic irreducible polynomial with coefficient in F2, which is x squared plus x plus 1. And this division gives you this this factoring. Okay. Yeah. So it's to check this, you can take this denominator and multiply it out with this quotient and check that it gets you x to the 16th minus x. But yeah, that's kind of annoying. All right. So this process, but there is a division algorithm that you can feed a computer, and I'll do this. Yeah. Okay. Don't check it. Yeah. There is an algorithm. There are fast algorithms that do this polynomial division in finite fields. So this gives a method for producing all of the irreducible polynomials over a finite field of so a finite prime field of degree d. And this is what I was saying. There exist efficient algorithms for factorization of polynomials mod p, which will give the individual irreducible polynomials. Right. So in Dummit and Foote, he delegates this to the exercises. But yeah, I don't think we'll go into this though. But you can do this if you want to. There are algorithms that factor polynomials mod p. That's all he says in the text, and leaves the actual algorithms for the exercises. And the importance of having irreducible polynomials over finite fields is that they give representations of the finite fields of order p to the n as quotients of these irreducible polynomials. You just take f of x, an irreducible polynomial with coefficients in f sub p, the finite field of p elements, and if f of x has degree n, which there always will be, and this recursive process is a way of constructing f of x iteratively, recursively, then you can represent f sub p to the n as a quotient of this. So this is a way to, like, I don't want to say physically, but like concretely write down f sub p to the n. You can build these polynomials, this irreducible degree d polynomials, recursively using this type of algorithm, and black box the algorithm about factorization of polynomials mod p. And once you build f of x, an irreducible degree d polynomial with coefficients in f sub p, then you have a representation of a finite field of p to the n elements. So now, not only do we know everything about finite fields, we can also represent them as quotients in a very concrete way, so we can work with them in, say, computer programs and stuff. All right. Now, this is a note about the isomorphism of different presentations of these finite fields as quotients of this polynomial ring by this irreducible polynomial. Since there is a unique finite field of p to the n elements, so for this specific cardinality, there's a unique finite field of that cardinality. Any two of these presentations where you have distinct irreducible polynomials are isomorphic because they represent the same finite field. So two different presentations are isomorphic. So let's construct an explicit isomorphism between these two presentations. Let's take f1 of x and f2 of x to be two irreducible degree n polynomials, and we want to write this explicit isomorphism between the first field that's isomorphic to f sub p to the n and the second field that's also isomorphic to f sub p to the n. So this is the first field as a quotient, presented as a quotient, f sub p of x, so the polynomial ring with coefficients in f sub p, modded out by the first irreducible polynomial, and this is the second presentation modded out by this. Oh, this is a second irreducible polynomial and the first. So we're trying to build this isomorphism. Okay, so the first thing to note is that the second irreducible polynomial splits completely in the splitting field. Because, as we said before, any irreducible polynomial Oh, never mind. So f sub p to the n is the splitting field for this guy, and f sub p to the n is isomorphic to um, the quotient ring, quotient field f, the polynomial ring quotiented by the other polynomial f1 of x. So since this is the splitting field of um, the second polynomial splits completely in the quotient field given by the first polynomial. So yeah, in this first presentation. So now there is some polynomial alpha of x, which represents an element of the splitting field. But now the splitting field is presented as this quotient. So elements of this quotient are polynomials. So there is some polynomial alpha of x, which is a root of this polynomial. Since this polynomial f sub 2 splits completely in the splitting field, there's this polynomial element of the thing that is representing the splitting field. And this is a root of f sub 2. What this means is if you take this polynomial alpha of x in this field that is presented as a polynomial ring mod this irreducible polynomial, and you perform f sub 2 of alpha of x. So you're taking this polynomial alpha of x and taking powers of it and whatever in the way deemed by f sub 2. So you feed alpha of x into f sub 2. You get a new polynomial, and that's going to be 0 in this quotient polynomial ring. And that's what we mean by this polynomial being a root of this polynomial. So that's kind of a weird thing, but yeah, this is a field. So the isomorphism between the two presentations of f sub p to the n is given by this map that takes x, which is a root of f sub 2 of x in this field, to alpha of x, which is also a root of f sub 2 of x in this field. Right, since both of these are simple extensions, you just take a root of this guy, which generates this polynomial, this field, to a root of the same field, to a generator of the same field. So this is also a simple extension. Okay, I feel like, yeah. If this didn't make sense, then I think you have to think about it a little bit more. So here's an example. F sub 1 of x is x to the fourth plus x cubed plus 1. And f sub 2 of x is x to the fourth plus x plus 1. So these are the two irreducible quadratics over f sub 2. So define a field with two elements. Wait. Yeah. So these are these two irreducible quadratics. So you actually have three irreducible quadratics, but let's just pick two of them. What are they? X to the fourth plus x cubed plus 1 and x to the fourth plus x plus 1. So x to the fourth plus x cubed plus 1, x to the fourth plus x plus 1. So these are just two, they're not the two, they're just two irreducible quadratics over f sub 2. Okay. All right. Then alpha of x is x cubed plus x squared is the root of f sub 2 of x. So you also have to check this. What do I mean by check this? Like you have to take, you have to check that it's a root of f sub 2 of x. So f sub 2 of alpha of x you have to check that this is equal to 0. Why is this 0? Because f sub 2 is alpha of x to the fourth plus alpha of x plus 1. And alpha of x is this guy. So you have x cubed plus x squared to the fourth plus x cubed plus x squared plus 1. And then you do all the computations. This has to work out because this is a second iterate of the square map, and we're in characteristic 2, so it distributes. So we get x to the 3 times 4 is 12 plus x to the 8 plus x cubed plus x squared plus 1. And then you have to show that this is 0 by continuing by reducing by um, x cubed plus x to the fourth plus x cubed plus 1. So yeah, you have to show that this is 0 in this ring by showing by taking out factors of this guy. Yeah, I'm not going to do this, but yeah. Explicitly you should check that that works out to convince yourself that this actually works out. So we have this isomorphism between this presentation and this presentation by taking the polynomial, oh no, by taking the polynomial, where are we? X to x cubed plus x squared. Oh, why does that keep happening? All right. So the last question in this chapter was, or section was about how many irreducible polynomials of degree n are there over fp. So the way he answers this is by using something called the Mobius Mu Function. So the Mobius Mu Function is 1 for n equals 1, 0 if n has a square factor, and minus 1 to the r if n has r distinct factors. And so there's this theorem about called the Mobius inversion formula. Oh no. And the Mobius inversion formula um, hold on. So the Mobius inversion formula says this: if f of n is a function defined for all non-negative integers n, and capital F of n is this function. We're taking the divisors of n and summing up f of d for all of the divisors of n. Then you can recover f of n from capital F of n by doing this thing, which is called convolution. You're taking the Mobius function and convolving with capital F of n. You're summing over the divisors of n and taking mu of d times f of n over d. Okay. And somehow this recovers the original function f of n. So yeah. And then we use this to count the number of irreducible polynomials of degree n over a finite field. So let's see how this is done. So let's do this. we take phi of n, phi of d, or rather psi of n, and say that this, oh no. Okay, so psi of n, let's define this to be the number of irreducible polynomials of degree n in the polynomial ring f sub p of x. So we want to count psi of n. So in proposition 18, we factored the polynomial x to the p to the n minus x as a product of, first you take the divisors of n, and then you take the irreducible degree d polynomials, and you take these polynomials, right? So this is proposition 18, right? And now let's look at the degrees on both sides of this equation. So taking the degree of this side, you get p to the n, and taking the degree of this side, you get the sum over the divisors of n, and now the product of the degrees of irreducible degree d polynomials. So each of the polynomials on this side have degree d, right? So that means this is going to be a power of d, or no, it's going to be a multiple of d, because every time you multiply a degree d polynomial, okay, it's going to be this, psi d times psi of d. So why is it going to be, why does this thing collectively have degree d times psi of d? Because there are psi of d irreducible degree d polynomials, because that's what psi of n counts. If you plug in n equals d, you count the number of irreducible polynomials of degree d in this polynomial ring, and each of them have degree d. So the total degree of this inner product is d times psi of d. So you get this. And now let's apply the Mobius inversion formula. For f equals, so, okay, let me write this down. Apply Mobius inversion formula for f of n is equal to n times psi of n, right? So f of n is just some okay, let's go back. F of n is just some function defined for all non-negative integers, and then capital F of n is sum over the divisors of n times f of d. And that's exactly what we have here. This thing is f of d, and we're summing over the divisors of f of d. So this thing is capital F of n, right? So that's kind of cool. And now we apply the Mobius inversion formula. So the Mobius inversion formula says we can recover f at like this. So we get that f of n, I'm just rewriting, is the sum over the divisors of n times mu of d times capital F of n over d. But capital F of n is equal to p to the n. So this is just p to the n over d. So we get this. And finally, this gives us a formula for the number of irreducible polynomials of degree d over fp, because f of n was defined to be n times psi of d. So this is n times psi of n. So therefore, psi of n is equal to 1 over n, 1 over n. So let's divide both sides by n. And what's on this side is the sum of divisors of d, mu of d times p to the n over d. So we applied the Mobius inversion formula to get a formula for the number of irreducible polynomials of degree n with coefficients in the finite field of order p. Okay, so that's all. Yeah. End the recording.